we go. I'm recording this for Remy. Everybody say hi, Remy.
Hey, what's up, Remy?
And actually, I will be, as we start to get into second semester, I do this on most of the lectures that we go through because the problems are tricky to follow by just looking at notes, and so I record a lot of the lectures and link them onto my calendar so that if you miss, you can go back and watch it, or if you just want to go back and watch us go through a problem, then you can do that. So just know that that's a resource. I don't really spend a lot of time doing that first semester, but second semester I do. So, starting today,
So that's neat.
It is neat.
That's helpful.
All right, so now,
I wish my math teachers did
I
that.
drank this morning beer.
in chapter 12, 12.2, it is all about something called a rate law. And a rate law is basically an equation. And the equation relates concentration, time, and reaction rate, kind of depending on which rate law we're talking about. So there's two different rate laws. I'll let you write those down. We're going to talk about those, and then specifically today we're going to go through that first one, the differential rate law. No, I missed it. Okay, so I had to think for a second when I looked at this why I put these in quotation marks, and then I remembered that there is a reason. It's not just there. On the AP test, when they ask you to do calculations of rate laws and stuff, they don't always specify differential rate law. They might just say find the rate law. And if they say find the rate law, they're talking about specifically the differential rate law. Sometimes they just don't say that part of it. They'll specifically ask for integrated rate law, or sometimes just IRL. So that's why. Now, these different rate laws, they're basically equations, like I said, that show how reactions depend on things like concentrations, time, and reaction rate. Depending on which rate law we're doing, shows a different relationship. And so the differential rate law shows how two things are related. How the rate of the reaction depends on the concentration of reactants. Now, we talked about concentration, remember, in brackets. With some reactions, if the concentrations change, then the rates also change. So, if you have less of a reactant, then all of a sudden the rate is going to be different. And so this rate law, this equation that we're going to come up with, is going to show how the rate of the reaction, the speed of the reaction, depends on those concentration changes. The integrated rate law shows how concentrations depend just on time. How does the concentration change over time? So today we're going to talk about the differential rate law. So the first thing we're going to talk about is just the general equation, and then we'll talk about how to find it specifically for each reaction. Okay, so the general format of a differential rate law equation is the rate is equal to K, and this is the first of about 10 different Ks we're going to talk about. But K times the concentration of, you know what, I should start out with this reaction up here. If the reaction is A plus 2B gives me C, okay, so I've got two reactants and a product over there. The rate law equation is going to have K, which is a constant, times the concentration of A to some exponent, times the concentration of B to some exponent. And that's the general format. So basically what we're going to be coming up with is we're going to be using experimental data to determine all the things within these equations. We're going to determine what the exponents are in this equation, and we're going to determine what K is. K is called the rate constant. The rate constant is kind of tricky because it's different for every single reaction. It's not like R in the ideal gas law where you plug in the same number every single time. Every single reaction has its own rate constant, and so you have to figure out what that rate constant is. And so there's a way to go through and figure that out. But you can only figure it out using experimental data. And sometimes that's like a multiple choice question. Like it might ask you, in which ways can you find K? And the answer is always, you can only find it using experimental data. And we'll go through the process of doing that. Let's see. One thing just to notice about the rate law equation is that it only includes the concentrations of the reactants. C, any products are not included in the rate law equation at all. So it's the concentration of each reactant to some exponent that you're going to find. All right, so there are different orders of reaction. There's zero order reactions, first order reactions, and second order reactions. You need to know what that means, and then we're going to go through the calculation. After we go through the process of how to write the rate law equations, one of the questions will also be like, what's the order of the reaction? And so you can tell that based on the equation and a few things, just knowing these definitions. So first of all, zero order reactions, they have a constant rate, meaning that the rate is completely independent of concentration. You can change the concentration of any of the reactants or products or whatever, and it's not going to change the rate of the reaction. That's a zero order reaction. A first order reaction is when the rate of the reaction is proportional to concentration of one of the reactants only. So maybe like if you change the concentration of A, then the rate of the reaction will change. And so that would be first order. Second order, there's a couple different options. You can have the rate being proportional to the square of the concentration, which is kind of weird, or proportional to the concentration of both reactants, A and B. And so if we're talking about just general equations and what they look like for zero order, first order, and all that kind of stuff, for first order, you might have, and we're still dealing with this reaction right here where we have A plus 2B gives me C. If the rate is equal to K times the concentration of A, and that's it. That's the rate law equation. That's first order because it's showing that the rate is dependent on the concentration of one of the reactants. I could also just have K times the concentration of B. That would also be first order. If I had something that looked like this, K times the concentration of A squared, that would be a second order reaction because the rate is dependent on the square of the concentration of A. And this is all general. When we start to like put in numbers and deal with experimental data and stuff, it'll probably make a little bit better sense. Also, second order, I could have rate equaling K times the concentration of A times the concentration of B. If you have an equation that looks like this, that is a second order equation because it depends on the concentration of A, but not only that, it also depends on the concentration of B. Changing the concentration of either one of those things would also affect the rate of the reaction. You can go beyond second order reactions, like you could have something like this. No, that would be a 2 right there. And that would be a third order reaction. Okay, basically you add the exponents. So 2 plus 1, that would be a third order reaction. For zero order, rate just equals K. Okay, so that's kind of generally what they look like, and we'll be coming up with those equations and identifying which order reaction they are, and that's what that means. All right, so K is the rate constant. Every reaction has its own rate constant, and every rate constant has actually different units depending on if it's first order, second order, third order, and all that stuff. And that's a really popular AP question, is to ask you what the units are of K. Sorry, there you go. All right, so all units of K. They're different depending on the order of the reaction. And like I said, it's a very common AP question for them to throw in, not only for you to find the value of K, but specifically what are the units for K. And I could just give you like a list of all the units for K, if it's zero order, first order, second order, whatever, and you guys can memorize them. But that's not super helpful remembering them long term. So I'm going to show you where the units come from. And it's not hard, and so if you can like figure out and understand where the units come from, then you don't have to memorize it so much. You can just kind of figure it out logically. So let's start with first order reactions. First order reactions are ones that depend on the concentration of one of the reactants. Okay, so let's remember what that equation looks like. Rate equals K times the concentration of A. Thank you. Now here's how I can figure out the units for this. I know the units for rate. Okay, we calculated rate on Monday. So what are the units for rate? Molarity over seconds, okay? So I'm going to do that. Molarity over seconds equals, and I'm just going to put parentheses right here to represent units for K because I'm going to figure those out. Units for A, I've got brackets around it. That's concentration. What are the units for concentration? What is it? Molarity, right? So my units for concentration are just molarity and that's it. And I'm just going to put over 1 just so I can kind of keep everything in a fraction. So if I want to go through and I want to determine what these units are for K, okay, here were my units for rate, here's my units for concentration. I want to figure out what the units are here. I've got to plug in something here in this empty spot that's going to give me units of molarity over seconds. I already have molarity on the top. What do I need on the bottom? Seconds. I need seconds to give me seconds right here. So if I multiply, and I can just put a 1 right here, if I multiply these units together, I get molarity times 1, that's molarity, over seconds times 1, that's seconds. So I end up with molarity over seconds. So my units for K in a first order reaction is 1 over seconds, or this way. They like it this way, okay? So just take it whatever's on the bottom of the fraction and just put a little -1 on the top. That means that it's like inverse of that. All right, so let's do second order. General equation for second order reaction is the rate is equal to K times the concentration of A times the concentration of B. These are the concentration of both of my reactants. I just go through the same process. So my units for rate, molarity per second, that equals my units for K, I'm going to leave blank for right now. Units for concentration of A is molarity. And units, I'll put molarity over 1. Units for my concentration of B, also molarity over 1. So I want to figure out what goes here so that I get units of molarity per second. Okay? So
1 over SN?
I need seconds, okay? There's no seconds anywhere over here. So I definitely need to have seconds on the bottom. And then if I multiply these on the top, I get molarity squared. But I have only 1 molarity. So I need to divide by a molarity, which then will cancel one of the molarities, and I'll end up with molarities per second. I have a 1 right there. So then my units are going to be seconds minus 1, molarity minus 1, which is just another way of writing 1 over seconds and molarity. All right, let me give you, I'm going to give you a third order because every once in a while they'll give you an equation like that and ask you to find units for K. So that general equation is rate equals K times the concentration of A and the concentration of B squared. Okay, now I want you guys to do it. I'll give you guys like 3 minutes right now just at your table and you guys can talk about it. Go through this same process that we did up here and see if you can figure out what the units for K are. Okay? A couple minutes and then we'll see what you get. I'm gonna. Do you want to? Yeah, I'll just. All right, units for K. I gave you an extra minute to like take a break before we do. All we have to do after this is the example of how to calculate the equation. All right, when you substitute in everything units for this, you have molarity over seconds here for rate. Solving for this one, this is molarity over 1. This is molarity squared over 1. So your units, you should have 1 over what should go on the bottom? M squared and seconds, right? So units on a third order reaction would be M minus 2, S minus 1. Okay, can you derive and come up with those units on your own? I mean, you'll deal with them enough to where you might have them memorized, but down the road, you might not remember them, but if you can figure out or remember how to do this, then it's easy.
Does it matter what order we have the M and the S?
No, you can put the S first and the M second. It doesn't matter. Okay, so here's the actual number part of this. Okay, all of these are just like general equations. Now we're going to apply it to actual experimental data and rates. And so these are the steps we're going to follow. Just write down the steps for now. They won't make as much sense until we actually do them. But then we're going to go through one example, and then I'll give you one practice.
How do you know which molarity to use like in that equation? Like, is it just like a general one that you would use for that, or
Like what number do you plug in?
Because like what if there's two different numbers and you know which one to plug in?
Yeah.
Okay.
Let's do this example, and then it'll probably make sense.
Okay.
Okay. Okay, I'm not even going to actually talk about these steps until we go through the example, but this can be used as kind of like a checklist as you go through these different problems, and just make sure that you're doing everything that you're supposed to do in order. And after we do the example, these steps will actually make sense versus now they just probably don't mean very much. So here's, and this is going to be a pain, you're not going to like this, but I do want you to write down this whole thing. The rate law problems, this is what they look like. You are given an equation, and you're given data from different experiments. So you're given initial concentrations of the reactants, and you're giving initial rates of the reaction for usually at least 3 experiments. And you use this experimental data, which is why I'm making you write it all down right now. You use the experimental data to go through and actually write the rate law equation, figure out if it's 0 order, 1st order, 2nd order, and find out the value of K, which is the rate constant. So I'll give you a minute to write that all down, and then we'll go through and show you what to do with all of those numbers. Oh, yeah, no, there should be. All right, so they give us this equation. I've got NH4, NO2 minus, and then I end up with nitrogen gas and then 2 water molecules. They give me, there's 3 different experiments where they start out with different initial concentrations of the reactants. Okay, so in the first experiment, they start out with an initial concentration of 0.1 molar NH4 and 0.005 molar NO2 minus. And then based on those initial concentrations, they measure the rate of, when they give you this initial rate, it doesn't really matter what it's like with respect to, so they don't really list that, but they would say the initial rate then of the reaction is 1.35 times 10 to the negative 7th molarity per second, and that's based on those initial concentrations. Then another experiment is done, and they give you the data from that. So with these starting concentrations, that gives me a reaction rate of this number. And then in experiment 3, I start with these concentrations, and that gives me this rate. So we're going to use all of that data to figure out what the rate law equation is. So step 1, which is actually, on this one it said to choose 2 experiments such that all but one variable cancels. There's actually one thing you have to do before that, and that is to write out the general formula of the equation. And the general rate law is, and we've written this kind of earlier in the notes, that the rate is equal to K times the concentration of, now in the rate law equations, it's reactants only. Okay, so if there's 1 reactant, then it's just 1. If there's 2 reactants, then put both. If there's 3 reactants, put all 3. All the reactants need to be included in the rate law, not products. Okay, so the concentration of my first reactant is NH4. Now here's where I'm going to actually put in specific stuff. NH4 is one of my reactants. I don't know what that exponent is right there. I need to figure out what that is. And then also times the concentration of NO2 minus to the y, which I don't know what that exponent is. I'm going to figure that out. Okay? So do that first. Always set up the equation first. Are there any questions about how I set it up like this? Just, yep, go ahead.
How do you know which rate reactions? I'm confused. How do you know which rate reactions you use?
like first order, second order, whatever, you don't know. So you set it up like this every time. You set it up with every single reactant, and then based on what you calculate for your exponents will determine what your final equation is going to be.
Okay.
So the next step after you do that, it says to choose 2 experiments so that one variable will cancel. Now, if you look at experiment 2 and experiment 1, I have numbers here that are the same. So I have 0.1 molar and 0.1 molar. So if I set one of those over the other, one of those things is going to cancel. That 0.1 is going to cancel. So what I'm going to do is I'm going to take all of my experiment 2 stuff and put it over all of my experiment 1 stuff. The whole purpose of that is going to be to solve for x and y. Okay, that's why I'm doing all of this, is to solve for x and y, which will tell me what order the reaction is. So I'm going to take my numbers from experiment 2 and put them in this equation. And then I'm going to put it over, and I'm going to take all the numbers from experiment 1 and put them in this equation. So we'll start with experiment 2. Okay, the rate from experiment 2 is 2.70 times 10 to the negative 7th. That's equal to K, I don't know. The concentration of NH4 is 0.1 to the X. The concentration of NO2 minus is 0.01 to the Y. Okay, all of that just came from this chart up here. And then I put that over, and I do the exact same thing. I do that with experiment 1. I take all of my numbers from experiment 1, and I plug them into the rate law equation. All of this so I can solve for the exponent numbers. The rate for experiment 1 is 1.35 times 10 to the negative 7th equals K. We're not going to know what K is yet. The concentration of NH4 in experiment 1 is 0.100 to the X. The concentration of NO2 minus in experiment 1 is 0.005, and that's to the Y. Okay, now what I want to do is I want to cross out everything I can cancel, or cancel out everything I can cancel, and then try and solve for one of these exponents, okay? So if I take 2.7 times 10 to the negative 7, and I divide it by 1.35 times 10 to the negative 7, you get 2, okay? You usually end up with some pretty easy numbers to work with, okay? Over here on the right side, things that will cancel, K's are going to cancel, so I can just forget about those and cross them out. The 0.100 to the X, those cancel, okay? So now what I can do is I can take my 0.01 and divide it by 0.005. What's that going to give me? 2. Okay, all of that to the Y. So you can solve for what Y is. Y equals what? 1, right? 2 to the first power is just 2. So I know that this exponent right here is going to be 1. So now I have to go through the same process again to try and solve for x. So I want to look for a situation where I can cancel out. I canceled out this side first so I could solve for y. So now I want to see if I can cancel things on this side to solve for x. The 2 experiments that give me something I can cancel would be experiment 3 and experiment 2. By the way, if there wasn't anything over here that would allow me to cancel, then that's okay, because you already know y. So just if you don't have anything that cancels, just pick 2 experiments and then plug in your y that you already know, and then you can just calculate it. Just requires 1 extra step. Okay, but these do cancel. So now I'm going to do experiment 3 over experiment 2, and I'm going to do the exact same process. Yep.
Why do we do experiment 3 over experiment 2?
Because if I do experiment 3 over experiment 2, then I get this side to cancel, and then I can solve for x. Because on the previous one, I had this side to cancel, so I solved for y. So I'm just trying to solve for both exponents. So, okay, experiment 3 data And again, I'm going to do it exactly the same way. The rate in experiment 3 was 5.40 times 10 to the negative 7 equals K. My concentration of NH4 is 0.2 to the X. My concentration of NO2 is point, sorry, I'm covering it, 0.010 to the Y. That's all just taking the data from experiment 3 and plugging it into the general rate law equation. I put that over experiment 2 stuff. So experiment 2 stuff, my rate is 2.70 times 10 to the negative 7 equals K. The concentration of NH4 is 0.1. That's to the X. And then my initial concentration of NO2 is 0.01 to the Y. So now different things cancel. So now, I mean, K's still cancel, but now the Y stuff cancels out. So I can solve for the X. So when you divide out these two numbers over here, these two rates, you get 2 equals 2 to the X. So X equals 1. So then my exponent for X is also 1. All of that, it's a lot of work, but it's to figure out what the actual rate law equation is and to figure out if both of these reactants affect the rate or not. If you ended up with any of these exponents as 0, then it would eliminate that thing from the equation. And so it's important to figure that out. Or if you got any of these exponents as 2, then it would show you that the rate depended on the square of the concentration of that particular reactant. But now that I know that the exponents are just 1, then my rate law, when it asks you to write the rate law, all it's asking you to do is say the rate is equal to K times, in this case, the concentration of NH4 plus. And the exponent was 1, so you don't have to write 1s, but it's just going to be there. And then times the concentration of NO2 minus. What this equation tells you once you figured out those exponents is it tells you that the rate of the reaction depends on the concentration of NH4. It also depends on the concentration of NO2. So if the concentration of either of those things changes at all, then the rate is also going to change. The reaction can slow down or it can speed up depending on how the concentrations are affected. By the way, just kind of a shortcut in figuring out the order of the reaction. If you add together the exponents, okay, I have a 1 and a 1 right here. This is a second order reaction. So if it asks you what order is the reaction, second order overall. And then they might say that it's like first order with respect to NH4 and first order with respect to NO2, like whatever those exponents are separately. Okay, there's one more step to this equation and then I'm done and we'll take a break. And that equation is to solve for K, or that question is to solve for K. You actually need to find a numerical value for the rate constant of K, and you can plug in any experiment data. It doesn't matter what experiment you choose. You could choose experiment 1, 2, or 3, and you're going to take that data and you're going to plug it into the rate law equation that you know. So I will choose, what do I want to choose? I'm going to choose number 1. So if I take my data from number 1 and I plug it into the rate law equation, the rate in experiment 1 is 1.35 times 10 to the negative 7. That equals K. The concentration of NH4 is 0.100. That's to the first power. And then my concentration of NO2 is 0.0050. That's also to the first power. Then you can solve for K. Then it's just algebra to solve for K. K equals 2.7 times 10 to the negative 4. Do not just leave the answer for K without units. Your K needs to have units. We talked about how to figure out what those units are. This is a second order reaction. We talked about that. You can look back in your notes, or you could go through and derive what those units are going to be. Molarity -1, seconds -1. Okay? Stop.